All right, welcome. Today, we're going to tackle a really fundamental question in AI. How can a machine possibly make smart decisions if it can't remember every single thing that's ever happened? The answer, believe it or not, is this really cool, kind of simple but super powerful idea that's all about, well, intelligent forgetfulness. Let's dive in. So let's start with a big question. Okay, so picture this. You're an AI agent, maybe a robot or some game-playing algorithm. To figure out the absolute best thing to do right now, do you really need a perfect photographic memory of everything that's ever happened to you right from the moment you were first turned on? You'd think more information is always better, right? Well, maybe not. And that question right there gets us to a huge challenge in AI, something we can call the problem with the past. I mean, just imagine our poor robot trying to keep track of every sensor reading, every tiny movement, every single outcome forever. How could it possibly sift through that endless mountain of data to make one good decision? It's not just tough, it's basically a one-way ticket to information overload. Now, to make any kind of decision, an agent needs a summary of its current situation. In a field of AI called reinforcement learning, that's where agents learn by, trial and error, we call this little summary the state. Just think of it like the agent's snapshot of the world at one specific moment. Okay, so here's the million-dollar question. What do we actually put in that snapshot? If we try to cram every piece of data the agent has ever seen into that state, it just becomes this massive, clunky thing that's impossible to work with. We've got to find a smarter, more efficient way to capture what's important. Well, lucky for us, math comes to the rescue with this really elegant solution. It's a simplifying assumption known as the Markov Property. It's basically a way to be, well, intelligently forgetful. To really get a feel for this, let's look at two games. Think about draw poker. In poker, you absolutely have to remember your opponent's history, right? Did they bluff last time? Are they a risky player? The past completely shapes your strategy. Now, switch over to chess. In chess, who cares how the pieces got to where they are? It's totally irrelevant. All that matters for your next move is the board right now. Chess has the Markov property. Poker doesn't. So if we want to get a little more formal about it, we say a state is Markov if it crams everything useful from the past into that one snapshot. Once you know the current state, the rest of the history just doesn't matter for figuring out the future. It's like the present puts up a wall, blocking the past from having any direct say. And that is the core idea, right there. If our agent's understanding of its state has this special property, we can just toss out the entire history. We can focus only on the now to make the best possible decisions. It's just this incredibly powerful shortcut. All right, so now that we have this amazing tool for simplifying things, let's see how we can use it to actually build a model of a decision-making problem. So whenever a problem has this special Markov thing going on, we can model it with this awesome framework called a Markov Decision Process, or MDP for short. And you should know this framework is the absolute mathematical foundation for a huge chunk of modern reinforcement learning. The part of AI that's all about learning from rewards and punishments. An MDP really just boils down to 4 key parts. First up, S for states. That's all the possible situations the agent could be in, like low battery or high battery. Next, we've got A for actions. Pretty simple. Those are all the choices it can make, like search or recharge. Third, P for probabilities. These are basically the rules of the game, telling us the chances of going from one state to the next. And finally, R for rewards. These are the points the agent gets along the way. Okay, to make this stuff less abstract, let's use a simple example. Let's imagine we have a little robot, and its whole job in life is to find and collect empty soda cans. Its entire world can be perfectly described as an MDP. Okay, let's take a second and really break down what we're looking at here. This diagram is literally a map of our robot's universe. The circles are its 2 states. Its battery can be high or low. The arrows are the actions it can take. So, follow me on this. If the robot is in the high state and it decides to search, 2 things can happen. There's a chance, let's call it alpha, that it finds a can and its battery stays high. But there's a 1 minus alpha chance that searching drains the battery and it flips over to the low state. This little map lays out every single thing that can possibly happen. So this table, it's showing us the exact same stuff as that diagram, just spelled out with the numbers. Let's walk through it. Check out the last row. If the current state is low and the action is recharged, the probability of ending up in the high state is 100% certain. The reward for doing that is 0. Okay, now look at a riskier move. If the state is low and our robot still decides to search, There's a beta probability that it just stays in the low state, but there's a 1 minus beta chance that its battery completely dies and it needs to be rescued. And bam, it gets hit with a big penalty, a negative reward of -3. Ouch. This table defines the physics of this robot's entire world. Okay, so now we've got this perfect little model of our robot's world. But that doesn't actually tell the robot what it should do. I mean, how does it figure out that being in a high battery state is way better than being in a low one? Well, the answer is this really cool concept called a value function. You can think of it as basically a scoring system. It gives every single state a number that predicts how much total reward our agent should expect to get in the long run if it starts from that state. So you can see how this works, right? A state with a high value, that's a good spot to be in. It's promising lots of future goodies. A state with a low value, on the other hand, is one you probably want to get out of fast. So the agent's goal becomes simple. Learn what these values are, and then just pick actions that move it towards states with higher values. And this right here, it's a perfect illustration of what I'm talking about. On the left, you've got a super simple little grid world. The agent gets a big prize for getting to square A. And on the right, you see the value that's been calculated for every single square. See how the numbers get bigger and bigger the closer you get to A? It's like the values create this invisible map, or even a slope, that just guides the agent right to the reward. Check out this other great example, this time from golf. Now in golf, a lower score is better, of course. These lines show the value of any spot on the course, which is just the number of strokes you'd expect to take to get the ball in the hole. The value is -1 when you're on the green, -2 when you're a bit farther out, and so on. So the player, our agent, wants to take shots that basically move them downhill along this value map, getting closer and closer to that hole. All right, let's bring it all home in our final section and see how all of these pieces, the Markov property, the MDPs, and these value functions all click together to build the very foundation of how an AI agent can learn. So let's just quickly recap the path we've taken. We started with this monster of a problem, an infinite history. We found a solution with the Markov property, which, remember, lets us be smartly forgetful. We then use that awesome property to build a formal model of our world, the MDP. And finally, we gave our agent a clear goal: learn the value function so it knows which states are good and can guide itself towards future rewards. And really, that's the core of it. These concepts, they're the absolute bedrock. If you can wrap your head around this logical flow, you've got the key to understanding how modern AI can learn to do incredible things, from defeating the world's best Go player to controlling a super complex robotic arm. And this kind of leaves us with one last big question to chew on. We've built this incredibly powerful way for machines to learn by intentionally telling them to ignore the past. It's a fantastic, efficient engineering solution. But what do we lose by simplifying things this much? By only ever focusing on the present, can an AI ever really get a deep, true understanding of how the world works? It's definitely something to think about, isn't it?